The last thing we did was acid and basic buffer. And now let us understand how the buffer gets affected if you add some small amount of acid or small amount of base. Okay, either we add strong acid or a strong base. Okay, so basically you have a buffer solution here. Let's say I have an acidic buffer here. All right, let me take an example. Like we have CH3 COOH combined with CH3 COONA. Okay, let's say the acid concentration is A, the salt concentration is S. To that we are adding a small amount of strong acid like HCl of X moles. Got it? You can call it in terms of moles or concentration, doesn't matter. So, but for our understanding, let us give that in terms of uh, X moles. The total volume here is V. V as the volume here. Got it? Now, after adding these two, right, solution will have CH3COOH, CH3CONA as well as HCl. Now, in that case, the type of equilibrium what we expect here will be one CH3COOH, which is in equilibrium with CH3CO minus plus H plus. So the concentration A and S here mainly. And what would happen the minute you add some amount of HCl? You're adding some X amount of HCl. Obviously, this is in a small composition. We are not adding a large amount, a small composition. On adding a small composition, now we will expect that CH3CO minus to react with HCl and convert everything into CH3COOH. Sorry, plus Cl minus. For example, CH3CO minus is S concentration or S moles. Okay. And HCl, let us say I have added X amount. So this is in a small amount, limiting amount. So there will be some X amount consumed here. This was already A. So now it will become, so it is already A. It will become A plus X. And this will be X amount. So basically this acid concentration increases. The salt concentration decreases by X amount of units. Here I'm assuming A and S as moles. Okay, so A moles here and S moles here. Now, if that is the case, what is the new concentration? The new concentration of CH3COOH, new concentration will be equal to A plus X. And what is the new concentration of salt concentration? That will be S minus X. Hence the pH new will be equal to pKa plus log of salt, which is supposed to be salt by acid concentration, which is S minus X by A plus X. So this will be the new formula, right? As compared to that of old pH. The difference in the new pH and old pH will be very small amount, but this will be the new pH formula. Clear, everybody? Right? Okay, just make a note. Right? So the content would be very similar. So imagine if the strong acid is being added. Okay, small amount of NaOH of B concentrate, sorry, NaOH of X concentrated or moles added. Clear? So in that case, now CH3COOH that would react with NaOH directly to convert this into CH3CO minus plus Na plus, sorry, uh, plus Na plus H2O. Got it? So in this case, this was already A moles, this was S moles, and now you are adding X moles of this one. Correct? X moles. Let me write this as X moles. Sorry, X moles added. So in that case, this will be losing out this X moles because NaOH added is in a very limited amount, and this will become S plus X. So in that case, now the acid concentration is moles is A minus X, and salt concentration is, salt moles is S plus X. So what do we have? So pH will be equal to, or pH nu will be equal to pKa plus log of salt concentration. Concentration is always, moles by volume. So the final volume is anyway going to get cancelled. So this into A minus X, which is in moles, divided by V. Volume term will get cancelled anyway. So that will be pKa plus log of salt plus X divided by A minus X. Okay. So this will be the new pH of the solution. Got it? So the only difference here is this one. Here it is S minus X by A plus X. Here it is S plus X by A minus X. That is the major difference you will get. Okay. Now sometimes instead of giving you in terms of, moles, you might be given in terms of concentration of a volume V1, V2 like that, of different volumes here. Then how do we compare? Now, imagine you have to compare that how much volume of HCl to be added, how much amount of volume of HCl to be added of a certain concentration. So in that case, let's say if concentration of HCl is given instead of number of moles, let's say we have m molar HCl added of volume V, V. In that case, what will be the concentration term? What will be the number of moles term now? Now, earlier, like I said, if you have a if you have an acid, let's say the original concentration is A by V1, and CH3CO minus will be S by V1. Okay, this was the original concentration. Now, the new concentration will be CH3COOH, correct? Will be, new concentration will be, because when you add acid, we just learned that the acid concentration will increase and the salt concentration will decrease by that amount. So now the new acid concentration will be equal to number of moles, which is A moles, correct? A moles minus M into V. These are the number of moles of HCl, that divided by total volume, which is V1 plus V, correct? This will be the case. So total amount of acid will be equal to, plus A plus MV by V, V1 plus V. Similarly, salt concentration CH3CO minus nu will be S plus Mv divided by V1 plus V. This is the total volume. Hence, now if you write the pH nu will be equal to pKa plus log of salt concentration, which is S plus Mv divided by A plus Mv. This will be the S minus, sorry, S minus Mv and divided by A plus Mv. Okay. Most of the time, questions will revolve around calculating the volume V. So in that case, this is the formula you will be using. If it is uh, acid added, okay. If it is base added, very similar formula, but this time salt will have an addition part, acid will have a subtraction part. I guess this is clear, everybody. Done. Now let's understand the term what is buffer capacity or buffer index. We use both these terms interchangeable, buffer capacity or buffer index. See, the amount of strong acid or a strong base that you are adding to change the pH of the solution by 1 unit. So that means this new pH which you are writing, it should be 1 unit different. Okay. So imagine original pH was 4. Now by adding an acid or adding a base, if the pH is changing to either 3 or 5, in such cases, how much amount of acid you added or how much amount of base you have added, correct? That per liter of the solution, remember that. It should be always about for 1 liter of the buffer solution, how much moles of acid or how much moles of base, strong acid or a strong base that you are adding to change the pH by 1 unit. That is called as buffer capacity or buffer index. So you can see it is delta N, which is the number of moles of acid or a base added divided by change in pH. Change in pH, if it is 1 unit, then the number of moles added is called beta, or such beta is called as buffer capacity or buffer index. Okay. So let us start understanding by adding some delta A moles of acid. Basically, it is the same thing which we have derived earlier here, correct? The X in this case, what I have written, that is what I'm writing it as delta A instead. That's it, correct? So in such case, now what can I say? First case, when you have small amount of acid being added, so pH before I add HCl, what is that? So before adding strong acid of before adding strong acid, the pH old pH old will be equal to pKa1 plus log of salt moles by acid moles. Correct? Let me put this as equation 1. Okay. And now, what is after adding? After adding the strong acid, external acid like HCl, correct? Now the pH new will be equal to pKa, sorry, this is pKa, is pKa plus log of salt minus delta A by acid plus delta A. Just like how I have written x there, s minus x by A plus x, here I'm writing it as delta A by A plus delta A. Now what is the difference? Delta of pH is equal to pH old minus pH new. Okay. Obviously, since you are adding an acid, we expect that the pH need to be decreased. So that's why I took old minus new. If it was base, it will be new minus old. Basically, you need a mod value. It doesn't matter how you take it. So in that case, what we will have here is pKa will get cancelled. I will have this as log of salt by acid minus log of salt minus delta A by acid plus delta A. Okay. Now can I write the same thing as this way? Log of A plus delta A by A minus log of S minus delta A by S. So all I'm doing is bringing this part here, sorry, bringing this part here and bringing this part here. So there is no harm in writing like that. So in that case, now what do we have here is log of 1 plus delta A by A minus log of 1 minus delta A by S. 1 minus delta A by S. Clear? If you remember the logarithmic expansion, log expansion of ln of 1 plus x. Clear? So ln of 1 plus x will be nearly equal to, because it would be something like a sum of all of this 1 plus x square plus x cube and so on. But these are all very small values, ignorant values. So that will be equal to almost same as x. Got it? That will be equal to almost same as x. If x is very small value than 1. So that is the same logic I'm applying here, that delta A by A is a very small value. And how do I convert a log into ln value? So you can see delta of pH is equal to 1 by 2.303 ln of 1 plus delta A by A minus 1 by 2.303 ln 1 minus delta A by S. And now notice 1 by 2.303, if I take it common, 2.303, if at all I take it common, now I can write this log of 1 plus delta A by X as delta A by A minus of delta minus delta A minus delta A by S. Okay, approximation. This is approximation. So that is equal to 1 by 2.303 into, you can see that A and A is getting added up here. Clear? So you will have this as delta A by S plus, sorry, delta A by A plus delta A by S. So delta A is coming out to be common. So delta A by 2.303 multiplied by S plus A by SA. And this is equal to delta pH. Now let me bring this delta pH to the left hand side and rest all of the part to the right hand side. So that implies I will get beta value, which is equal to delta A by delta of pH. That is equal to 2.303 SA by S plus A. And isn't this the definition what we're looking for? Buffer capacity, which is the amount of acid added divided by change in pH. That is defined as buffer index. And what did we get that value? We got this as 2.303 SA by S plus A. Okay. Hence, this is the formula we will be using. Beta is equal to 2.303 into SA divided by S plus A. Okay. So this is a reasonable way of identifying how much is the buffer capacity of any given buffer, knowing what is the salt and acid concentration. Of course, if the beta value is higher, note beta value increases, which means buffer capacity increases or better quality buffer. Better quality buffer. Please finish the writing part, everybody. See here in this formula, whatever delta A you're using, that should be for 1 liter of a solution. Remember, delta A here is per liter of buffer solution. Got it? So suppose if you are writing some 20 millimoles of HCl for 200 ml of 200 ml of buffer solution, correct? In that case, you have to scale it to 1000 ml. Understood? So for 200 ml, if it is 20 millimoles, for 1000 ml, how much will be the acid you have to add? So like that, you have to scale it and accordingly calculate the beta value. Okay. Hmm. Now let's come to this understanding that if at all there is a particular buffer solution and it is being given at a different cases or different concentrations. So I took total 5 cases. First case, when the acid concentration, the original weak acid of buffer, its concentration is 0.1 molar, salt concentration is 0.01 molar, while second case here it is 0.2 and 0.05, here it is 0.5, zero point 0.5, here it is 0.1, zero point 0.1, and here we have 0.01 and 0.001. Got it? Now, in all of these cases, let us calculate what is the value of beta. Okay, so you can see what is the value of beta here. So beta will be equal to, 2.303 multiplied by, because 2.303 is common, I'm just taking the ratio here. So it is S plus A divided by SA divided by S plus A, correct? That is what we learned it as a formula. So now let me do that. 0.1 into 0.01 divided by 0.1 plus 0.01. Okay. So what do we have here? We have 10 raised to power of minus 3 divided by 0.11. Got it? This is the value we have. Next one, this is 0.2 multiplied by 0.02, that whole divided by 0.22, isn't it? So that will be like 4 into 10 raised to power of minus 3 divided by 0.22. And here we have 0.5 into 0.5 divided by 0.5 plus 0.5. So that will be equal to 0.5, I mean 25 or 2.5 into 10 raised to power of minus 1. This is how much we will have. Divided by 1, that is going to be, uh, simply divided by 1. Here we will have 0.1 into 0.1 divided by 0.2. So here we have 1 into 10 raised to power of minus 2 divided by 0.2. And here we'll have 0.01 into 0.001 divided by 0.011. Okay. Now if you compare all of these values, this will be 1 into 10 raised to power of minus 5 divided by 0.011. Now if I call this as beta 1, beta 2, beta 3, beta 4 and beta 5. So if you compare the buffer capacities, okay, capacity wise, you will clearly notice that beta 3 value is the highest, then beta 4, then we have beta 2, then we have beta 1, and lastly we have beta 5. Correct? So using this, we could say one thing for sure, right? Using this, we can say one thing for sure, that if at all we have a higher concentration of acid and salt and equal concentration, that is most important, higher concentration as well as equal concentration, then the chances are you will end up with high buffer capacity. That means the quality of buffer increases if we have a higher concentration of acid and base, as well as you have almost equal concentrations of acid and salt. Got it? Now, if you notice this wallet, okay, you can see my wallet in my hand, right? So the wallet is made out of leather. Okay, my watch, this is made up of leather. Correct. So the polishing on this leather, on this watch, if you notice, correct. So this is also a buffer solution. Got it? But the polishing is always made with a higher concentration of buffer and having both acid and salt concentration of almost equal amount. This way, the resistant of the solution to hold any amount of acid which is spilled on it or a base spilled on it, that it will be able to resist the pH, change in pH. That's why most of the strong buffer solutions, for example, any acrylic paints, that is also a mixture of, salt and acid. But the mixture of them will be high concentration with almost equal concentrations. And that way you can increase the capacity of buffer. I guess this part is understood, everybody. Right. Now, without approximation, suppose if at all I have to figure out what will be the value, of buffer capacity, clear? Then how would I write that? Check out. Sorry, here I think I have written it. No, no. Here in this space, let me write down that. See, what if I want to write delta pH, clear? Without any approximation, without any log approximations, if at all I have to write, I'll be writing this as 1 by 2.303 into ln 1 plus delta A by A minus ln 1 minus delta A by S. Correct? So that implies I can write it as ln 1 plus delta A by A divided by 1 minus delta A by S, which is equal to 2.303 into delta of pH. And now, if I take this 2.303, and sorry, let me put everything in log only. I mean, there is no point of writing that in ln here. So log only, log of 1 plus delta A by A divided by 1 minus delta A by S. So that is equal to delta of pH. This is what we learned from the start. So now, if at all I take the anti-log on both sides, so I will get this as 1 plus delta A by A divided by 1 minus delta A by S. That is equal to 10 raised to power of delta pH. This will be 10 raised to power of delta pH. And If I multiply that on both sides, 1 plus delta A by A is equal to 1 minus delta A by S multiplied by 10 raised to power of delta pH. 10 raised to power of delta pH. So from here, if at all I take delta A common on both sides here, I mean after multiplication, I will get this as 1 by A plus 10 raised to power of delta pH divided by S is equal to 10 raised to power of delta pH minus 1. Okay. So from here again I can calculate, delta pH, I mean delta A by delta pH. If at all I divide everything by delta pH, again I'll get one more formula. Got it? This is without approximation. Clear? So it doesn't matter whether you add with or without approximation, the values will be very close by. Got it? But in case if you have to use that formula, use this one. Okay. Right. Now notice what is buffer index. While we define buffer index, we always write the delta pH as 1 because the change has to be 1, right? So then buffer capacity is always about 1. Buffer index is what we write it as delta A by delta pH. And now notice how the beta value changes with respect to pH here. So pH and how the beta value is changing. Okay. So how the beta value changes here. See, usually it will go like this. It will take up a turn like this. And then it will go like this. Okay. So typically here, this value and this value, if you notice, this would be at pKa minus 1. This will be at pKa plus 1. And this value, the peak value, the highest value will be at pKa. Okay. Which clearly shows that this is the best buffer range. This is called the best buffer range, where the buffer is acting at its best potential. Of course, the best is at pKa value, but across, if you notice, pK plus 1 and pK minus 1, it will act as the best buffer solution. So we call it as a buffer range. So buffer range, where it acts as the best part, is pKa plus or minus 1. Okay. So this is the value where the buffer acts as the best one. So notice I have written that note also: when acid and salt are at high concentration and equal concentration, buffer quality is the best. Everybody done?
1 second, can you go up?
Yeah.
That's it.
Let's come to the understanding of titration. What is a basic, first acid-base titration. And based on acid-base titration, we can discuss, how to figure out what are indicators and as well as how to use them. See, usual setup of titration is that we will have a stand to which there is a fixed instrument called as burette, and below that we can have a flask or a test tube in which you already have some component, and one component will be added into the burette. Now, usually what we do in titration is we take a known value of volume V1 of either acid or a base, having some known value of concentration, which is N1. So let me put that into the tube already. And everything that is known value which you are taking in a tube, that is called as titrand. That is called titrand. And then you are adding an unknown concentration of either acid or a base into the burette of some volume which has been added. Now, what you are doing is while the titration is being done, here you are measuring how much amount of volume you used. Correct? So, you would be measuring what is the volume that you are using here to figure out the end point or the neutralization point. So, a point where the acid and base are equal amounts in terms of their equivalence. So if N1 V1 are the equivalents of this component which is known one, and N2 V2 are the equivalents of the unknown one here. If these two are equal, that is called neutralization point or equivalence point. And using the equivalence point, you can figure out what is the unknown concentration. And this is what is the main setup that we do via titration. So here V2 is measured after the titration is been done. But now the question is, if at all I have to measure V2, I need to know when to stop, right? That means I just have to open the tap, and as it starts, mixing with it, you just need to know when to stop. And once you stop, you can measure V2, and thereafter you can calculate N2. To do that, first realize two things. Acid base reactions are extremely fast. Okay. So that means instant reactions. As soon as the acid hits with the base, immediately salt formation will take place. And both acids and bases are generally colorless. In such case, we need to add some composition here which will make a color change, especially at neutralization point. That means when you reach the neutralization point, that means when the number of equivalents and of acid and base becomes almost equal, at that point there must be a color change. And if you are able to get that color change, we call it as indicators. Correct? So that small thing which you add to this flask here or test tube here, that is what we call it as indicators. Notice indicators themselves are actually acids and bases. So they themselves are weak acids and weak bases. Got it? But they are usually organically derived. So most used indicators for us, in general, is phenolphthalein, which is a weak organic acid. Next, methyl orange, which is a weak organic base. Got it? Everyone clear? Right. Clear? Now, notice what is phenolphthalein and what is methyl orange. Although the structure is not asked right now, correct? Going ahead, when we do the organic reactions, we will come across the preparation of phenolphthalein and uh, methyl orange. Now, notice the structure. Usually, what is the structure like? You'll have a benzene form here, and then you will have a phthalic anhydride which is connected with another two benzene rings with OH, and here it is connected with another OH. This is the structure of phenolphthalein. Okay. Similarly, if at all I write the methyl orange form, so methyl orange typically will have, you know, cyclic structure like this. I mean, the benzene structure like this, right? So with dimethyl amine here, aniline here. and this is connected with N double bond N, connected with another benzene, which is connected with SO3 minus Na plus. This is called methyl orange. Got it? Start knowing it from right away. I mean, from this topic only. If you can start learning, it will be better, because by the time when we come across organic reactions, you will know exactly what is the structure of methyl orange and phenolphthalein. Okay. Done. Now, these are the two indicators that we have been adding. Clear? So, what will these indicators exactly do? Alright. And how would that help? Check. If at all, I have, let's say, phenolphthalein taken for our purpose, just for sake of understanding, let me take phenolphthalein. All you need to do is very small amount. That means one or two droplets of phenolphthalein that you have to add it into that uh, test tube. Okay. As soon as you add, what you will realize is HPH. HPH is a way to write that this is this entire thing. In short, we are writing it as HPH. H as in acidic part, pH as in the conjugate base part. Here, MEOH, the base part, I'm writing it as OH minus, and the rest of the part is Me. That means this is just for our understanding, we have written it as MEOH. So if I take HPH, what do we expect? It will ionize as H plus and pH minus. Of course, it is a weak acid, so it will have some Ka value. Now the Ka value, I'm writing it as K in as an indicator. So for K in, how do we write the K in here? K in will be equal to H plus concentration into pH minus concentration divided by HPH. Okay, HPH here. Clear? So here this HPH is the unionized form, and this is the ionized form, ionized form. Okay. And in the case of phenolphthalein, the unionized form is colorless. When the composition is more of unionized form, it is colorless. When it is completely ionized, it is going to be colored, which is pink color. Okay. Somebody is at the door. Just give me a second. So we have the unionized form of phenolphthalein and ionized form of phenolphthalein. Now the pH of the solution can also always be written in terms of these two. That is, you can see it here. The H plus concentration of the solution will be equal to K in into HPH concentration divided by pH minus concentration. If I take log on both sides, minus log on both sides, so I will get this as pH of the solution, which is equal to pK in plus log of pH minus divided by HPH. Or we can simply write this as pK in plus log of ionized form, ionized form divided by unionized form. Okay, ionized by unionized form. So how much is the ionized amount divided by how much is the unionized amount? That decides what is the pH of the solution. Okay. So we can always relate pH of the solution with respect to the amount of ionized and unionized form of phenolphthalein. And that will only give you the color. Usually what is the norm that you need to check is for a naked eye, you will see a distinct color when the concentration of either ionized or the unionized is dominant by 10 times. Okay, that means this ratio has to be either 10 by 1 or it has to be 1 by 10 so that both their colors will be distinct. Got it? So, for example, here pH of the solution, pH of the solution will be equal to pK in plus or minus 1. pK in plus or minus 1. Just like in buffer capacity, we learned it that the best buffer range is pKa plus or minus 1. Similarly, here also, if the pH of the solution is around pK in plus or minus 1, then we say it is uh, you know distinct colors which has been observed. Okay. For instance, when it comes to phenolphthalein, for HPH, that is phenolphthalein, the pK in value is 9.2. It is 9.2. What does this suggest? 9.2 का मतलब क्या है? Let's see. If let's say this is a pH scale and pH scale has somewhere 9.2 here, then we have 10.2 here, and then 8.2 here. Here we have 7.2. Here we have 11.2 and so on. Okay. Which means if the pH of the solution is above 9.2, that is 10.2 and above here, correct? Then you will notice the color of the solution will be pink. From here onwards, it will be pink like this. So this direction, it will be always pink color. Okay. While if you go to the other direction here, yeah, you will notice on this side, if you go, 8.2 and below, if you go 8.2 and below, it will appear to be colorless. So as long as the pH of the solution is around 9.2, it will be mild pink color, okay, light pink color. So it will be like a mix of this one and this one, mix of these two. So that will be the light pinkish color here. So in this range, let me write down that part here. So from here to here, it is like mix of these two colors. So that will be light pink. So you would notice that complete pink is observed as you have 10.2 and above, and complete colorless is observed 8.2 and below. And this is typical uh, range of phenolphthalein. So phenolphthalein will have this color range. Everybody clear? Likewise, for methyl orange, the pK indicator is 4.4. Approximately, that is 4.4. If it is 4.4, and now you see the color line, this is the color line. Let's say on this color line, this point is 4.4, and this is 5.4, 5.4, and here we have 3.4 and below. Okay, so in such case, you will notice 3.4 and below. Here you will see red color, while 5.4 and below, you will see this as yellow color, and in between, you will notice this as the orange color. Okay, so that's why it is called methyl orange. So here we will have complete red color, that is below, if you are going towards the left hand direction. If you go towards this right hand direction here, which means above 5.5 or above 5.4, it will be yellow color. And somewhere between 3 to 5, 3.4 to 5 approximately, it will remain orange color. Okay. I've written that already here. So I'll just delete this part. Check. So using this information, I can say color range, color range of phenolphthalein, HPH, HPH is between 8 to 10. Okay. And color range of methyl orange, correct? This is around 3.4 to 4.5. Why I'm saying 4.5? By the time it comes to 4.5 and above only, right, it will start showing that coloration. Okay. So here the orange is less dominant, yellow is more dominant. It will almost appear like yellow color from the start. This is practical value. Theoretical value, it should be 3.4 to 5.4. Okay. Practical value is almost 3.4 to 5, 4.5. Just above 4.5, you will start seeing yellow color. I hope all of you got a sense of what is the indicator and how does it play the role of colors in solutions. Now, this is essential to understand when to stop the titration. Got it? So now, let us try the titrations one by one. Imagine if at all I have to make an acid-base titration. Clear? We have four different types of titrations we can perform. One is strong acid, strong acid, weak acid, strong base, and finally weak acid, weak base. So we start with strong acid and strong base titration. So let us assume titrand which you are taking is HCl, titrant which you are taking is NaOH, and HCl volume which I am taking is 10 ml, concentration is 0.1 molar. NaOH is of 0.1 molar concentration, and V volume is the volume which you are adding over time. During the titration, you are adding that. Okay. For this situation, what do we do? First, let us assume volume of NaOH is 0 ml. 0 ml means at the start of the titration, just before the start of the titration. What is the pH of the solution? pH of the solution will be minus log of H plus concentration. And H plus concentration, because it is a strong acid, so it is minus log of 0.1, because only HCl is present at that point of time. Hence, pH is equal to 1. Clear? So we got the first point, that is pH is equal to 1. Next, second point, when the volume of NaOH, let us assume is 5 ml. I have added 5 ml. Then I am measuring what is the pH. Okay. So to do that, first you need to understand what is the reaction happening. HCl plus NaOH is going to give us NaCl plus H2O. And HCl is fixed, which is 10 ml into 0.1, these many millimoles. NaOH now it is 5 ml into 0.1. So this is 1, this is 0.5. This is limited amount. So 0.5 will be left, 0.5 of salt and water will be formed. And you know that the salt which is coming from strong acid and strong base, it does not undergo hydrolysis. So here there is no hydrolysis happening. And you know that only HCl will contribute to the pH, and HCl is 0.5 millimoles. And since the number of moles is known, I know the concentration nu. The new HCl concentration will be equal to number of moles divided by total volume. Total volume is now 15 ml. So pH will be equal to minus log of H plus concentration, which is 0.5 divided by 15 ml. Okay. So that is equal to minus log of 1 by 30. Okay. Or simply pH will be equal to plus log 30. Okay. So that will become 1.48. So have you noticed there is, after adding 5 ml, the increase in the pH is very gradual. Okay. It's not very high change also. Okay. But it is gradually increasing. So pH is around 1.48. The first two cases are clear, everybody. Now, imagine I added, volume of NaOH has 10 ml. If I add 10 ml, now what will happen? So, in the case of 10 ml, for the same reaction, correct? Now you would notice this as uh, 10 into zero point 0.1, and this is also 10 into zero point 0.1, which clearly suggests that both of them will get completely uh, reacted, and you'll have only 1 millimole of NaCl left. That means it is a complete neutralization happened. No acid is left, no base is left, number of equivalents are same. Okay. So at that point, what is the pH? If you calculate, pH will be equal to 7, right? Why? There is no acid left, no base left, and NaCl is not hydrolyzed. So what should be the solution? pH of the water, because pH of neutral solution is how much? 7. So pH value is 7 here. And let me write one more case. Suppose if you have volume of NaOH being added as 12 ml. If it is 12 ml, then what will be the case here? So that is HCl plus NaOH is giving us NaCl plus H2O, and this was 10 into zero point 0.1 and this is 12 into zero point 0.1. So this will get over with, and you will have this as 2 millimoles left, correct? So this will be 0 0.2 millimoles left, okay, and 1 millimole of NaCl form. Okay. So now what will be the remaining amount? Remaining amount is NaOH. So we have OH minus concentration, or NaOH concentration, is equal to zero point 0.2 divided by total volume. Total volume is 22 ml. So it is 1 by 110. Okay. 1 by 110. So POH will be equal to minus log of OH minus concentration, which is equal to minus log of 1 by 110. That is equal to log of 110. Okay. Log of 110 is, I mean, let us take this as approximately 100. So that means it is very, very close to 2. So if pH is close to 2, what will be the pH? pOH is 2. Then pH value will be equal to how much? 14 minus 2, which is 12. Got it? This is what happens. Okay. Now, guys, let us understand one thing. In that case, what should happen? See, if I, if you notice the four case values here, let me mark them. What is the pH values here? 1, it is going through 1.48, it is going through 7, it is going through 12. Correct? What did we notice? Initially, the rise is very slow, but suddenly, as you approach the volume as almost 10 ml, the pH drastically increases. Got it? And that's what I'm trying to express. If you plot pH versus volume of NaOH, if you plot pH versus volume of NaOH, now how does it vary? So it would go something like this. From here, it will start moving, gradually increasing. And thereafter, suddenly there is a rise in the pH of the solution. And it will keep on rising, and then start moving like this. This is the way it will start moving. Got it? So you can see there is a drastic change in the pH value here. So if I compare, this is the point where we have 10 ml. This is when the volume of NaOH is 10 ml. Okay. And if you compare this particular point, sorry, not here, somewhere at the middle, here, this is pH being 7. This is pH 7. Okay. And you can see up to 12, I mean, just in 1 or 2 ml here, this value here, this range is just small change in the volume, correct? It is like this. It is almost 9.9 ml. Here it is 10.1 ml. 9.9 ml and 10.1 ml. In that range, how much pH value got changed? Almost this is somewhere close to, I would say this one is somewhere close to 2 and this one is somewhere close to 12. Just between these two values, how much volume of NaOH we used? Hardly 1 ml. Between 2 to 12, 2 to 12, almost imagine. The ml difference is how much? Hardly 1 ml here and there. Either it is 9.5 ml to 10.5 ml. Within that 1 ml range, the pH of the solution suddenly shoots up from 2 and all the way to 12. Clear? Now imagine your setup, right? You are doing titration with phenolphthalein. Okay. So imagine this setup with phenolphthalein. First, using phenolphthalein. Using phenolphthalein, you know that initially, till volume of NaOH is close to 9.9 ml. Okay. pH remains, pH changes from 1 to hardly 2. Okay, 1 to 2. Let me just put it as 1 to 2. Okay. therefore therefore solution remains colorless. With phenolphthalein, you know that if the pH value is 1, 2, 3, 4, up to 8, it is colorless only, right? So it will remain colorless. But as volume of NaOH reaches to 10 point, maybe 10.2 ml and above, pH changes. pH changes from, right, 1 from 2 to almost 12. 2 to almost 12. Therefore, solution change color to pink. So understood? The pink coloration is within that 1 ml difference. This side it is colorless, this side it is completely pink. Okay. So it's very easy to figure out the color change using phenolphthalein. So how do we normally do the titration? We always keep adding small amount of NaOH and we shake the test tube and see whether there is any color change. Okay. So in the case of phenolphthalein, as you are very close to the solution, as you're very close to the neutralization value, you will see sudden color change will happen. Just with that small droplet of 1 ml, from the colorless, immediately it will become pink color. And that's an indication that there is a neutralization point reached. Okay. So yes, using phenolphthalein, we can definitely recognize because the range of change in pH is drastic. From 2 to 12, itna range change hota hai. So phenolphthalein can be used as a very good indicator. Similarly, using methyl orange, okay, pH changes from 2 to 12 2 to 12, then methyl orange color changes from okay, red to yellow, correct? So the solution was red all the time, and suddenly as it becomes the neutralization point, immediately it will start becoming yellow. So from here, what we can say, from based on this, what we can conclude is both phenolphthalein and methyl orange are suitable indicators, suitable indicators for strong acid and strong base titrations. So you can use any of this uh, indicator, and that will be acting fine, especially in this pH range. Please go through it, everybody. I hope all of you understood the strong acid, strong base case, how the pH is changing. Next case is about weak acid, strong base titration. Now, this is an important case. If you have a weak acid, strong base titration, okay. I took for an example HCl as a weak acid, NH4OH as a strong base. Got it? The titration setup is the same. That means in the burette, in the titrant, we are using HCl now. It is VML volume of, uh, you know, 0.1 molar. And in the flask, we are taking ammonium hydroxide of 10 ml volume and 0.1 molar concentration. Okay. The Kb value for this is given as 10 raised to power of minus 5. Okay. Expected uh, reaction is ammonium hydroxide plus HCl will become ammonium chloride plus H2O. Okay. So let's start with the first case. Case 1 is when the volume of HCl added is 0 ml. 0 ml means when there is only NH4OH. When in the solution there is only NH4OH, what is the pH? pH is equal to, it is a basic formula if you remember Oswald's dilution law, half of pKb minus log C naught, because there is only weak base present. For weak base, weak base formula, sorry, for weak base, this is the formula used. So pH is equal to half, sorry, POH, this is not pH, POH, yeah. POH is equal to half of pKb value is 5 minus log of 0.1. So that is equal to half into, this is 5 plus 1, 6. So how much it is? 3, which implies the pH value is 14 minus 3, which is 11. So we started off with first pH, which is 11. So solution में सबसे पहले the pH was initially started from 11, everybody. Okay. And now let's do the second case wherein the volume of HCl that you have added is, let's say, 2.5 ml. So I've added up to 2.5 ml. Now, how does it change? So basically, this reaction is what is happening right now. So in which we have 10 ml into 0.1 molar, which is fixed. And here you added 2.5 into zero point 0.1 molar. So obviously this is 1 millimole, this is 0.25 millimole. So this will get over with and you will be left with 0.75 here, and you will be having 0.25 forming. Now notice the solution. How does it appear? It appears like a buffer solution because I have a weak base and its conjugate acid salt. So solution has turned out to be buffer now. So when you add 2.5 ml, the solution looks like a buffer solution. Now how do we calculate the pOH? So pOH is equal to pKb plus log of salt by base concentration. Buffer formula. So pKb value is 5 plus log of salt. Salt is 0.25 and base 0.75. So which is 5 plus log of 1 by 3. Okay, so which is 5 minus log 3. Correct? So it is 5 minus log 3. So that is equal to 4.52. Now this is pOH. What will be the pH value? pH value is 14 minus 4.52. So that is equal to 9.48. मतलब समझ रहे हो ना? From 11 onwards, it is very gradually decreasing. It is not a drastic decrease. Of course, it should not be decreasing very strongly because it is a buffer solution. Okay. So it has to go a little slow. So wouldn't this case be strong acid, weak base? Achha, sorry, I wrote weak acid, strong base. Yeah, sorry. This is strong acid, weak base. Yes, it. Okay. Check. This is the pH value. So now we are slowly decreasing the pH as the titration is, happening further. Furthermore, as the titration proceeds. Now notice the third case. Now let's see what is the third case. If the volume of HCl, what you're adding is, let's say, 5 ml, then NH4OH plus HCl is giving NH4Cl plus H2. Now we have this as 10 into 0.1 and 5 into 0.1. This is used as 1 millimole and this is 0.5 millimole. And this will get over with, this will be left with 0.5 millimole. And this will also be forming 0.5 millimole. So salt concentration is 0.5, base concentration is also 0.5. So in that case, what is the pOH? pOH will be equal to pKb plus log of salt by base concentration. So pKb value is 5 plus log of salt is 0.5, base is 0.5, which is equal to 5. So pOH is equal to 5 and pH is equal to 14 minus 5, which is 9. Okay. So when it is at a best buffer, you know what is a best buffer? We discussed this, right? When the acid and salt concentration are equal. Correct. When they are equal, then the pH value will be equal to pK value. Here, because we are writing pOH, it will be equal to pKb value. So this is the best buffer. When you have a best buffer, what is the pH? pH is equal to 9. Okay. So we got first 3 points. Now, let's see the fourth one. Fourth one is a case. Fourth one is a case where the volume is 10 ml. So in such case, what do we have? NH4OH plus HCl. It's giving NH4Cl plus H2. So here, this is also 10 into 0.1. This is also 10 into 0.1. Both will be done and you'll have 1 millimole of ammonium chloride. Now notice there is no acid, sorry, no base, no acid, only salt and water. You have only salt and water. And in only salt and water, the salt is coming from a weak base. The species which is coming from a weak base will be strong. Hence, here it can undergo hydrolysis. So, NH4Cl can undergo hydrolysis. So, you know that hydrolysis of hydrolysis of strong acid weak base, strong acid weak base salt, correct? For that, what is the formula of pH? pH is equal to half of pKw minus pKb minus log of C naught. C naught is the salt ion concentration. So NH4Cl concentration, which is same as NH4 plus concentration, will be equal to 1 millimole divided by total volume. Total volume now added is 20 ml. So this is 1 by 20. So pH will be equal to half of, okay, pKw, which is 14 minus 5 minus uh, 1 by, sorry, log of 1 by 20. Okay. So this is 9 minus 1.3. So that is going to be 10.3 divided by 2, which is coming as 5.15. You can see it is less than 7. Okay. But notice one thing. Suddenly, the pH of the solution has dragged down. It was gradually changing, right? 11 से start हुआ था. It is slowly going from 11 to 11 point, I mean 10.5, maybe 10.3, 10.1, then 9. So as it comes close to that 9, after that adding that one extra droplet, suddenly it falls to 5.15. Okay. So hence what we can say, as the volume start, I mean as it is coming close to that neutralization point, there is a drastic drop of pH. And let me write the last case, fifth one. When the volume of HCl is, let's say, 12 ml, I took eventually everything at 12 ml. So for 12 ml, what can I say here? When HCl added is 12 ml, so we have this as 12 into 0.1. So this will get over with. You will have here as 0.2 millimoles left. And here we will have 1 millimole form. And obviously, when you have a acid present, there is no salt hydrolysis we should consider. So now the pH value which you calculate will be only on the basis of HCl concentration. So HCl concentration left will be equal to 0.2 divided by total volume, which is 22, or it is 1 by 110. So pH is equal to minus log of 1 by 110. So which is log of 110. Approximately this is like log 100. Log 100 means pH is equal to 2. So therefore pH value is very close to 2. So from 5.15, it is dragging down to 2. Okay. Right. So first check out all the cases, everybody. This is how you need to analyze the titrations, everyone. 1 to 5. Check if everybody got these values. Okay. So the first value is 11, 9.48, 9, 5.18, and 2. Is this good, everyone? Check. Now, if at all I put the graph I kept it down here. Yeah, take a little up. Now let us plot the graphs. So I'll put the values here. First case value, second case, third case, fourth case, and fifth case. So first case value, we got it as 11, 9.48, 11, 9.48, and then 9, then 5.15 and 2. These are the values at different volumes of HCl. So we need to start from 11, correct? And then how does it go? Check out how does it go here. It start moving like this, almost remain constant as a buffer form here, and then drastically decreases from here to here, and from there it will start moving like this. So this is the typical way you will notice the graph varies. Okay, and somewhere here at this point you will notice the neutralization point, which is how much we got that value as 5.15. 5.15. Okay, this is 11, correct? And the point at which this drastic shifting is happening is very close to 9. This is approximately close to 9 value here. Okay, so after 5.15 suddenly you will see the dragging of values into 2 and towards 1 and so on. So the color change is happening especially at this volume area, I mean at this particular volume. Okay, volume exactly at this point here is how much when the pH is this is at 10 ml. Okay, right. In the graph, what you need to remember is this area, this space here. I mean, from let me take different color from here, from this point to this point here, from here to here. This is called as buffer zone. This is buffer zone. This entire thing will remain as buffer. Okay, and this is the equivalence point. Okay, equivalence point is also called as end point. End point when you are doing it practically. When you perform it practically, you're supposed to get exactly, I mean, volume as at 10 ml, you should get pH as 5.515. End point, because you're doing it practically, it will be slightly above or below. Okay, so that's why practically the closest point to that equivalence point is called as the end point. Now tell me, if at all using phenolphthalein as the indicator, what is the issue here and what would happen if you have methyl orange being used? Using phenolphthalein, notice this one. Initially, we started off with 11, and 11 means the phenolphthalein color is almost light pinkish color. Sorry, complete pink color. And from that pink color, it is slowly starting to convert into here. The color is fading out. Pink color is fading out. It is reached 10. And from 10 onwards, as it reaches to 9, the color is almost colorless. You'll hardly see any color. Okay, I mean, because the minute you start going down the 10 value here, the color will be almost fading out. By the time it is reached 9, you hardly have any color left. So which means using phenolphthalein, you will end up titration somewhere at this volume only. Okay, somewhere at this volume, sorry, somewhere here, maybe somewhere here you will end the titration. But is it the correct volume for endpoint? No. Therefore, using phenolphthalein, you will not be stopping the titration at the correct point. But what if it is methyl orange? If it is methyl orange, 11, 9, 8, 7, everywhere the color is yellow only. So from here, it will be yellow. It will be yellow till this point also. And at this point, around 9.9 ml, the minute you add just 1 ml, from yellow, it will suddenly become orange. As it becomes almost 5.15, it will almost become orange. And just add one more extra droplet, that means around 10 to 10.2 ml also. It will become 2, correct? So extra 2 ml, we got that into pH close to 2. So as it becomes 2, it will become red. So that means you know that exactly somewhere between orange and that red color, we will have the endpoint. Hence, methyl orange is the more suitable indicator for this case. So using phenolphthalein, okay, it's difficult, it's difficult to find endpoint. So not a suitable indicator. Is not a suitable indicator. But using methyl orange, using methyl orange, it is a suitable indicator. Everybody clear? Right. Let's go to the next titration, which is weak acid and strong base titration. Now, the titrant which you are taking is NaOH. Titrant we are taking is acetic acid. The K value, N1V1, N2V2 values are given here. So at different volumes of NaOH, we need to figure out how the pH is changing. Okay. So everybody, please start working along with me. So start with the first case. You learned the rhythm of the question already, right? So volume of NaOH. First, you'll check out the volume of NaOH starting with 0 ml. If it is 0 ml, only weak acid is left. So for weak acid, we know the formula half of pKa minus log C naught. This is the formula. So that is equal to half of pKa value is 5 minus log of 0.1. So which is 3. So we are starting the pH. We are starting the pH from 3 onwards. So this is the first case. Second case is when the volume of NaOH, when the volume of NaOH is, let's say, 5 ml. At 5 ml, what do we expect is NaOH plus CH3 COOH will react to form CH3 COO minus Na plus H2O. So here NaOH is 10 into 0.1 and this is 10 into 0.1. Sorry, 5 into 0.1 and that is 10 to 0.1. So this value will be over with, correct? And what about this one? This will be left with 0.5 millimoles and you'll have 0.5 millimoles of this one. So you can notice that we have an acid, weak acid and its conjugate base salt. So what has this become? Acidic buffer. Okay. Solution is acidic buffer now. For acidic buffer, how do we calculate the pH? pH is equal to pKa value plus log of salt by acid concentration. pKa is 5 plus log of salt is 0.5, acid is 0.5. So this is the best buffer form. So this is the pH where the buffer acts as the best buffer. This is case 2. Now let's notice case 3. Case 3 is volume of NaOH added is, let's say, 10 ml. If it is 10 ml, then in the reaction you will not notice that you will notice that there is no NaOH left over. Everything is converted into salt. So this is 10 into 0.1 and this is also 10 into 0.1. So neither base nor acid is left, only 1 millimole of salt is formed. So what is the concentration of CH3CO minus salt ion concentration? Will be 1 millimole divided by 20 ml. Okay. Now how do we calculate the pH? Because it is undergoing, solution is under salt hydrolysis. Now what is the formula for salt hydrolysis? So pH is equal to, half of pKw plus pKa plus log of C naught. So that is equal to half of pKw is 14 plus pK value is 5 plus log of 1 by 20. So it is 19 minus 1 point, 19 minus 1 point, what is that? Sorry, 19 minus 1.3, correct? So that is 17.7 divided by 2. So which is coming out to be 8.85. Of course, it has to be greater than 7 only. Okay. Because you are making a salt hydrolysis of weak acid and strong base. pH has to be greater than 7. Next, let us check out the value of NaOH at 12 ml. At 12 ml, the complete titration has been already done and you are adding the extra moles of NaOH. So you would have this as 12 into zero point 0.1, 10 into zero point 0.1. This will not be left. 0.2 millimoles will be left here and 1 millimole of salt will be formed. And therefore, pH will be equal to minus log of OH minus, sorry, POH. POH will be equal to minus log of OH minus. OH minus is 0.2 divided by 22. So this is approximately minus log of 1 by 110. Or it is plus log of 110, which is approximately equal to log 100, which is 2. So pH value will be equal to 12. Okay. So now again you can clearly notice that how the pH value is changing. It has started changing from 0 to 5, 3 to 5, then 8.85, and then to 12. So I think all the 4 cases are sorted, everybody. Let's see how graphically the pH changes. So as you compare the pH here now, how does it vary? See, it starts from somewhere 3, correct? And from 3, it will almost go through a buffer solution range. And from there, suddenly there is a drastic increase here. And as it goes from here, it will start moving like this. So this is how the pH value varies. Okay. So this is the space where you will be reaching the neutralization. Okay. And the value here is, this is the value where it is 3, correct? And somewhere at the middle here, we have the neutralization point. Somewhere here, we will have neutralization point. And here, somewhere at this point, there is a drastic change here from almost uh, from here to here. Hardly any ml is being changed, but the pH drastically increases. The pH at which where it happened, you know, is 8.85. That is the equivalence point or the end point. What is the volume at which it happens? 10 ml. Finished, everyone? Right. Now notice, what is the best suitable indicator here? See, suppose if I'm using methyl orange, okay, using methyl orange, okay, if at all I'm using methyl orange, what would happen? Initially, the color is almost red. I mean, from red, it will slowly start turning into orangish, correct? And just here, before even coming to 10, we have reached the point 5. This is almost 5. So that means it has already become yellow. So the color change has happened here only, right? In the buffer zone itself. So let me point out this entire thing. This is buffer zone. This is buffer zone. And within the buffer zone, we notice that there is a color change. So you can say that color change is happening within the buffer zone. Color change occurs within the buffer zone. Hence, not a suitable indicator. Next, using phenolphthalein. So in case if I use phenolphthalein, see, initially from 3 till 5 up to this point, it is colorless. From there onwards, as you start increasing by just 1 ml, it will go all the way towards 12, correct? So this value is 1 where you are getting it as almost 12. So within this 5 and 12, there is a color change, isn't it? And that is just passing 8.85, which means yes, this is the best zone where the color change is occurring. So phenolphthalein is definitely a suitable indicator. Okay. So color change occurs at the uh, at the volume close to close to neutralization point. Got it? Hence, suitable indicator for titration. So for this titration, this is the most suitable indicator. Everybody. I hope all of you understood this logic. Right. The last thing is about weak acid and weak base titration. Got it? Here, none of them is suitable indicator. No calculations required here. You just need to understand that directly. None of these remain to be suitable indicators here. Okay. So let me just take up the uh, graph here now. So if you take this as the pH change versus volume of NH4OH added. NH4OH added. So most of the time it will remain like a buffer only. So that means it will drastically, there is no drastic change here. So it will stroke very gradually like this. And there will be slight change here like this. And then again it will go gradually like this. Okay. Gradually like this. Okay. So you can see there is no sudden change of pH. It will not happen as a sudden change of pH. You can see this entire range is where you are noticing the pH change values happening. So this is not a sudden change volume where it can be uh, observed. So any indicator which we take is not good enough. Any indicator we take is not sufficiently good enough to make any color change here. So hence we can say neither phenolphthalein HPH nor methyl orange is suitable indicator for weak acid and weak base titrations. So I guess all of you understood this point, right? So this is about titrations.